stupid mistakes. I've decided against stepping through the proof in here, but you should look on page 865. The middle of the page is the proof. You've got to love the name of this theorem. This is the theorem we're actually just applying. It's called the ballpark theorem. And they actually go into why it's called the ballpark theorem. You should take a look at the proof because it's stuff. Some of it's stuff we've already done. A part of it's kind of like a rehashing of a proof we already did, but it really shows you why the gradients have to be scalar multiples. Just don't want to get into it right now. I want to get into chapter 13. It's going to be hard to have any questions until you actually try this section. So I would get into 12.9 and try it out. Because I got to wait for specific questions. That each problem could be a little different. It's a little hard to show you a general case, right? Each one is kind of a different kind of approach, possibly. So like I was saying before, chapter 13 at least starts off really, really nice. We'll see if you agree with me. Let me pull this dude up real quick here. So in calculus, where did the integral actually come from? What do you do first before you take that step to the integral? Well, okay, antiderivative. Where does that come from?
The rectangles.
Rectangles, I like it. So an integral ends up being a sum of a bunch of rectangles. What? I can't add rectangles, but I can add their areas. Cool. So it's a sum of a bunch of areas of rectangles, right? You can do Simpson's rule and trapezoidal and all that kind of crap, but it's basically the sum of simple geometric figures, areas. So what do you think it's going to be now?
Squares, cubes.
Yeah, it's going to be cubes. It's going to be volumes, right? My inputs are going to be in the xy plane. So my inputs themselves are going to be areas. So I'm going to talk about, some point in this xy that sets up a height, and it's going to be the volume of that little cube. So I want to give you a better picture than I can ever draw on the board. Okay.
People say I'm the best typer. Jeez.
Sometimes you even hit the right keys.
Yeah, I just tell them I spend most of my time backspacing.
I type really fast. There's none of them words. It's just a collection of letters. Okay. Oops. Sweet. All right, here we go. So it starts off with, I want to get right to the idea. Let's see if this has the little... Oh, yes. There's no way I could possibly draw this up here so we could all see what the hell's going on. And it looks like the computer's having at least as much trouble as I do. Okay. That's informative.
Yeah. Well, I think it's that one.
Hey, there it
Black
is.
box.
Wow.
Now, what does it look like? You guys, let me see if you guys have the same comment as last semester. You guys ever seen that thing that's sitting in like weird little gift shops and something, and you could put like your hand in it? That's what it always looks like to me. Like you put your face in it if you're really bold. Who knows whose hands have been in there? So I would suggest not to do that. So here's the idea, and this is not the easiest thing in the world to see, but this is the shape, and these are the approximating rectangular solids, I guess we can call them. that if I added up all those, it would be an approximation to the volume of the whole thing. The volume under the surface. You guys with me? So that's what integral should mean in 3D is volumes, because now I have the surface that has itself as an area. Underneath that would be a volume. How do we know so far? So the weird thing is, one weird thing is, let me show you, let me get to the weird thing here. Before it was, this came from, get my words out. This came from this limiting process, remember? Of course, I equals 1 to n, f x I, delta x. Right?
Yeah.
Does that sound familiar? So of course, the summation symbol, which is an elongated s for sum, so that's the integration symbol, came from this summation. There's an fx, there's your dx instead of delta x for the width, because you're allowing the width to get infinitesimally small. So that's the whole idea. I want to rehash one maybe, which I just did. Now what's going to happen here, though? How many summation symbols do I actually need? I kind of disagree with the way the book did it, although they do it, it gets a little more to the point. But yeah, you actually sort of need 2. So now it's going to look like this. I equals 1 to n, j equals 1 to m. This is not what the book's going to have, by the way. They have something. They have one summation symbol. This makes more sense to me. F of x, I, y, j. And what you can't see here, if I can turn it all the way around, what am I actually looking at there? It don't say this volume.
Area on the top.
Where is?
Yeah, I'm actually looking at it from below because I wanted to be able to see how they broke up the XY plane. This is my inputs here, right? So now instead of talking about a 2-dimensional figure and I've got this little delta x, right? And then you can maybe do the midpoint or whatever. Remember that beautiful stuff? Or the left and right endpoint. But now I'm talking about this little area times, now what's got to go here though? This is what?
That's your domain.
This whole thing. It's a point. And more specifically, like here, what was this guy's here? What is this guy's whole meaning? Together, this should be an area. You're adding up areas. This is a width. This is a height. So it's the same thing. It's still a height. Doesn't it tell you how far up you are? Where the z is? You guys with me? So that's the whole thing. That's what I'm trying to prepare you for. The x and y are just inputs. My output is the height, where the z is. Up here, down there, wherever the hell. So that's a height. What do I have to have here to make it a volume?
Area.
Don't get too far ahead, but an area. So I'm trying. This is actually more general. I don't know if you guys remember or were taught that this is actually not always true. I don't know, did anybody know that? That is not always true for every function. There are certain functions that this does not work for. Right? Believe it or not. So the same thing holds here. This only works for, actually this works for most functions. There are just a few freaky ones that this doesn't quite work for. This infinite sum. You remember good old 280? Infinite sums, infinite series. They don't always work out to be something you can write in closed form. So this is sort of the same idea. Some functions just don't lead you to that. Most functions definitely work. So this actually is going to become and what the hell is that? Visually, what is this? What am I integrating over? Not quite. It's got to start with R, I'm sure, but it's a region. So it's the region that I'm integrating over. So this region might be negative, like 2 to 2, 2 to 4, 3 to 5, whatever. They got to identify the region. Section 13.1 is all about rectangular regions because those are obviously the easiest ones to work with, right? Rectangular regions. So this would be, for example, this might be A to B, C to D. One side goes from A to B, the other side goes from C to D. Okay, how are we doing so far? So that's the connection. That's what we've already done in Math 180. So we're not going to go through the same steps, thank God, of connecting this to that. But it's actually pretty much the exact same steps we took here. Still a limiting process. In this case, both n and m have to go to infinity. Oh boy, you pushed it. How much do I want to get in there? Oh. So here's the last thing I want to say. Because this is really nice. This is actually a little bit, there's a whole other way to look at this. It actually makes a little more sense. Why didn't you start there? It's here. So say I wanted to integrate, I want to get the volume under this surface. The problem is, I've got two different directions I can go, basically, right? I can go x and y, and of course any combination of those two, but I basically have two different directions I can go. So it seems like there's no real organized way to do this, but we've already done the organized way to do this. I can get a cross section. So if I hold x constant somewhere. Now trust me on this. So let me throw it all the way to the end. If I hold x constant, if I make x equal to b, whatever the largest it could be is, if I hold x equal to that, can't I get this area here just using Math 180? With me? But now how do I get the volume then? So that would be integral from Java to Perl. No. Integral from, what would be the integral from to? If I hold x constant here, what's allowed to change? Y. So I would want to integrate from C to D. Right? What goes here? dy. Because y is what's changing. You with me? Now that's obviously not enough. It's nowhere near enough because that's just the area under that curve. How do I get the volume under the surface then? If I take one step over, doop. Actually, let's take a bigger step so it's easier to see. That area is going to be a little bigger now, isn't it? Because my surface actually goes a little higher. So all I have to do is, this itself is going to end up being a function. Because I'm letting x be constant and y is varying. So x is going to still be in there. What's x doing? Going from what to what? From A to B. So then I would take this. This is each cross-sectional area. I want to say this, I want you guys to get this. That represents each cross-sectional area. I have to add all those up. So I have to integrate those.
A to B.
And that's what you said earlier. This, of course, makes sense to be this, because what's my little dA going to be? It's going to be dx times dy. That's going to be my little infinitesimal area. You with me? Okay. So the actual work, especially for section 13.1, is silly easy. Integrate with respect to what in this case, in the inner? See, so these go together. So x is held constant. Then whatever you get at the end, let me do one quick example. Let's say I had this here, right? So you look at the innermost integral. What do you get when you integrate that? What am I doing with respect to? Y. So I get x squared y. Good, because that's a constant, right? So it has to pick up a y when I integrate it. Minus y squared. From,
3 to 4.
and I'm right here, I'm a little more specific for myself. Because trust me, you start throwing these things in the wrong variable. Very easy to do. You with me? So I'll be very specific. I'm like, oh, I just did dy, so that dy equals 3 to 4. That's the outer integral. Cool. So inside I would get 4x squared minus 16 minus 3x squared plus 9. You with me? And then you just do that integral from 1 to 2. So the actual nuts and bolts of this, and actually the idea isn't too hard. And the nuts and bolts of this is beautiful, as long as they don't throw any weird shit in here, like trig substitution or something, which you will see a little bit of.